Hey everyone, welcome to this explainer. Today we're doing something really cool. We're drawing this wild parallel between humanity's very first information technology and the cutting-edge digital infrastructure we use to actually study it today. We're literally tracing the data lifecycle from clay all the way to the cloud. And it's a journey that shows us just how much our administrative systems have changed, but also, kind of surprisingly, how much they've stayed exactly the same. Right off the bat, let's dive into a massive question. How do you solve a 5,000-year-old worldwide jigsaw puzzle? Like, seriously, how do we piece together shattered administrative hard drives from the ancient world when those pieces are currently scattered across the entire globe? Let's figure it out. Section 1. First Data Infrastructure. So, to really grasp this puzzle, we have to look back at the original IT. I'm talking long before actual writing even existed, over 5,000 years ago. Ancient accountants in booming urban centers, places like Uruk, they had a problem. They needed a way to track their exploding economies, right? And you can't just keep all that in your head. So they came up with this brilliant 3D token system. They used these geometric clay tokens to represent specific amounts of commodities. And then they enclosed them in spherical clay envelopes called boule. It was basically an early physical tally system. Literally the earliest form of physical data storage, locking the economic truth of a transaction right inside a ball of clay. Well, over time, these early accountants realized, hey, we don't actually need these 3D tokens. Instead, they started mapping those physical tallies onto a flat 2D clay surface. Take the ancient Shim-Tukanag ledger formula, for example. They divided the clay tablet into distinct columns to isolate debits, credits, and net balances. It was an incredibly strict, structured formula. And guess what? Today, we call that modern architecture. I mean, it's relational databases using double-entry bookkeeping and distinct column arrays. The crazy takeaway here is that this ancient Mesopotamian framework was a super rigorous ledger system that functioned exactly like the relational databases we build today to audit modern supply chains. It's the exact same thing. Section 2. Ancient errors in clay. Now, as sophisticated as that system was, this infrastructure had some pretty major failure points. Researchers from the CDVAK project actually refer to these as shadow algorithms. Basically, hidden failures lurking in the data. Because, let's face it, ancient bookkeepers weren't perfect machines. When researchers analyzed R3 labor accounts, they found that scribes frequently messed up. They suffered from defective calculations, used completely invalid labor quotas, or just followed faulty algorithms. We see documented anomalies like the famous Erlenmeyer 155 tablet that show errors coming from unpracticed hands. These mistakes deviated entirely from the established footprint of uniformity they were supposed to follow. And this brings us to a highly specific and honestly very costly error: 227 and 2/3. In one particular ancient ledger that was calculating the work of a standing milling crew over a 12-month period, a scribe made a faulty artificial administrative calculation. The result? Exactly 227 and 2/3 fewer workdays were recorded than expected. They literally shortchanged the institutional ledger. It's wild. It really just goes to show you that a bad algorithmic formula can completely crash your data and ruin an audit, whether you're working in Microsoft Excel today or, writing in wet clay 4,000 years ago. Section 3. The Worldwide Jigsaw Puzzle. Okay, so imagine trying to audit those ancient bureaucratic errors today. It is incredibly tough when the original hard drives have literally crashed, broken into a million pieces, and been scattered across the globe. Thanks to centuries of archaeological excavations, historical looting, and honestly just the passage of time, we're left with thousands of cuneiform pieces distributed across completely isolated museum collections. To put that in perspective, fragments from the exact same archive in Uruk are split between the National Museum in Baghdad and Heidelberg University in Germany. Or the Atrahasis sea tablet, one piece is sitting in the British Museum in London and another is hanging out at a museum in Geneva. Because trying to physically reassemble pieces separated by thousands of kilometers is pretty much impossible, historians now have to rely on a process called virtual provenance tracking to reunite them. Section 4. Algorithms Rebuilding History. To actually pull off this virtual tracking, researchers are leaning on some incredible tech. Looking at the flat, 3D geometry of heavily eroded clay is unbelievably hard to read. But by using techniques like photometric stereo and combining that with depth-based shading and PXRF, which is essentially the chemical fingerprinting of the clay itself, the software mathematically darkens the deeper recesses of the tablet. So it takes this highly eroded, almost invisible surface and just dramatically reveals those hidden wedge impressions. Suddenly, boom, the ancient data pops right out at you. But how do you put these continents-apart puzzle pieces back together? Well, traditional assembly algorithms actually fail here because eroded break lines don't perfectly interlock like a fresh puzzle piece out of the box. Instead, the Virtual Cuneiform Tablet Reconstruction Project, or VCTR, uses this novel four-step automated pipeline. First, it calculates the boundary curves and fractures on a 3D mesh. Then, it projects that 3D boundary into a flat 2D range image, uses an in-painting algorithm to computationally guess what the flat surface progression should look like, and then back-projects it to 3D. Finally, it uses massive GPU acceleration to assess what's called a cost function based on the distances between points on the joining surfaces. It can evaluate millions of possible spatial alignments to prove physical joins across entirely different continents, all without a human ever laying a finger on the fragile artifacts. How cool is that? Section 5. Modern Digital Archiving Limits. Now, while it's absolutely amazing that we can reconstruct history using supercomputers, historians studying this digital shift are actually issuing a pretty stark warning. They point out that the very efficiency of digital search across these vast collections brings a real risk, the risk of overemphasizing whatever is most easily found. And in doing so, it undermines slower, more context-bound forms of knowledge. When we bypass immersive reading and place-based learning, we run the risk of losing that deep, multi-causal awareness of history. Sure, we might find the data way faster, but we risk stripping it of its actual deep meaning. On top of that, researchers who are trying to automate the analysis of these massive datasets face some severe operational risks of their own. If you use modern toolkits, like Google Notebook LM, for example, you run straight into API fragility. You're relying on undocumented code that can break instantly with just one tiny update. Automated batch exports constantly hit rate limits, which causes generation hangs or just total crashes. And perhaps the most ironic part of all this, because unofficial automation technically violates modern terms of service, researchers are explicitly forced to use dedicated burner accounts just to mitigate the risk of having their primary professional profiles suspended by a tech giant. We're quite literally building the future of historical archival research on incredibly fragile, shifting digital ground. Which leaves us with this ultimate paradox. Will our current digital archives, our undocumented APIs, and our burner accounts actually survive the next 5,000 years as well as those baked clay tablets did? We're sitting here using supercomputers to expose ancient scribes making math errors. But clay, it turns out, is remarkably patient. Code? Yeah, not so much. Think about that the next time you trust your most important data exclusively to the cloud. Thanks for joining me for this explainer, and I really hope this changes how you view the data all around you.